Hello and welcome to today's video. Today we're going to be taking a look at switch debouncing. First, let's begin with taking a look to see exactly what bouncing is. If we take a look at a typical switch circuit and how it's connected to the microcontroller, we can see that point A should be at 5 volts when the switch is open and 0 volts once the switch has been pressed. Now let's actually take a look to see what happens. Once the button is pressed, the voltage falls to 0 but bounces once or twice before finally settling at 0 volts after about 10 microseconds. Once the switch is released, bouncing can also occur in the opposite direction. Now we understand what switch bouncing is, we can take a look at ways to eliminate it from our design. The first step is going to be to add a low-pass filter. This will help eliminate the unwanted effects of the switch bouncing. I'm going to modify the prototype board with the low pass filter just to show you the effects. Unfortunately, with my large hands it can be quite fiddly trying to put in these small components, especially when I'm trying to do this behind a camera. Okay, so there's the capacitor and the resistor in place. Now I'm just moving the jumper which takes the signal into the Arduino. So I'm moving it now between the resistor and the capacitor that I've just added. Now we can see the effects. Before there was a couple of bounces when the button was depressed. Now after adding the filter, they've been removed. Now in practice we could leave it there and everything will work absolutely fine. But if we wanted to, just for fun, we could add a Schmitt trigger. This will actually clean up the edges, the rising and falling edges of the signal. The way they work is, if you have like a ramping signal on the input, you don't really want to feed that to the microcontroller, which is digital 0 and 1. So a Schmitt trigger basically has two thresholds, a 0 threshold and a 1 threshold. Now on a ramping signal, as soon as the voltage on the input hits the threshold of the 1 on the Schmitt trigger, it will immediately drive the output from 0 to 1. Also on the falling edge it will do the reverse. So as the signal on the input gradually decreases, the Schmitt trigger will keep it high until the 0 threshold is reached, at which point the Schmitt trigger will immediately drive the output low. So this just provides a very clean high or low state for the microprocessor to process. Now also remember that not only is this a Schmitt trigger, that this is an inverting Schmitt trigger. This means that if a low signal is applied to the input, a high signal is generated. And if a high signal is applied to the input, a low signal is generated on the output. Now we can see the complete solution. When we press the button, if we take a look at the oscilloscope, we can see a couple of things. So the green is the output from the Schmitt trigger, the yellow is the input into the Schmitt trigger. So what you can see with the pressed one is the button, the voltage is high, it starts to decrease. Because of the capacitor there's a slight curve to the end of that. But the Schmitt trigger completely eliminates that. As soon as the threshold is hit, it drives the output high because it's an inverting stage. And the opposite is true when the button is released. Now for this circuit the Schmitt trigger really isn't required, but I've just included it for your reference. It sometimes is very useful to be able to clean up a slow rising edge or a slow falling edge to convert it into a cleaner digital signal. That's the end of the video, so thank you for watching. If you have any questions, please leave them in the comments below.